All right, we've wrapped up talking about continuity and discontinuities in some sense. I actually kind of wanted to dig in and talk about a specific way you could have a non-removable discontinuity, and also kind of revisit one of those bad limiting behaviors that we talked about back in section 1.3. So you recall that I mentioned then that if a function happened to be unbounded near a target point, that the graph blew up. I got ready to point at a graph I never drew on this board because I did that with a calculator. Um, anyway, but yeah, you get that you got that shape of a graph that's blowing up forever and ever amen, or alternatively is shooting down in that direction and dropping eternally. That as we said, that the limit didn't exist. As it turns out, in those circumstances, we can actually give some slightly more specific nomenclature to this. I should also say at this point that unlike some of our previous sections, I actually have posted in Moodle kind of a guided note-taking exercise. So yeah, it's a PDF. You might find it useful. So that way, it just kind of guides us through the types of examples that I'm looking at, saves me from having to write down big long definitions on this whiteboard because you've seen my handwriting. I don't have much room. Anyway, so if it turns out that we have one of those unbounded things, either our limit is approaching infinity, or positive infinity if you prefer, if it's doing this number, flying up, up, and away. If it's going down, down to Goblin Town, then we would say that the limit is in fact approaching negative infinity. So you'll see the notation in there. Like I'm assuming you're familiar with the the 8 turned on its side, as notation for infinity. So you got that there. The definitions on the handout are a little precise. You don't need to worry too intensely about them. I think you kind of get the idea of increasing or decreasing without bound. So, one thing that you will also notice in there is it gives a precise, calculus-driven definition of what it means for a function's graph to have a vertical asymptote. You may have noticed that I've drawn some things that look like vertical asymptotes or maybe horizontal asymptotes, and I've intentionally avoided mentioning them. That's why. Without calculus, it gets awkward to describe what those are. So, anyway, so we'll talk about vertical asymptotes and horizontal asymptotes a bit more freely going forward. But so now I want to take a look at some of those examples as we roll through this handout here. So we have we start with actually evaluating some limits. So the limit as x approaches 3, 1 over x minus 3, quantity squared. I'm not going to be digging in really precisely here, necessarily. You may notice that if you try the direct substitution stuff like we've done before, you get a 0 denominator. That's bad. Non-zero numerator. Nothing is bringing it under control. And I had said the limit doesn't exist. That hasn't changed. Saying that a limit is approaching infinity or negative infinity doesn't magically make the limit exist. It's just describing a particular type of badly behaving function. Anyway, so you might try sketching a graph of this guy, and it turns out you have sort of like the classic anthill kind of thing where it starts out really, really small right here. We get toward 3, and then boosh, flies off. Then it comes back down on the other side, and it starts doing that kind of thing. And you probably would have at some point in the past kind of traced out like a little dotted line in between the two to indicate that asymptote thing. So in this instance, again, you could check this just as readily by using a table of values and feeding in 2, 2.5, 2.9, like we've done in the past, and you'll see those numbers keep growing and growing and growing without any conceivable cutoff. So this overall limit, we would say, is in fact approaching infinity. So that's an example of that in action. So the next guy on the handout is actually a little bit cleaner in terms of what it's working with. It just says 1 over x, so we want the limit as x approaches 0. The catch is, this time around, it's not quite so clear. If you sketch a graph of y equals 1 over x, you can do that if you'd like. Have that calculator. I'll wait. All right. So your graph isn't quite doing the same thing on opposite sides of 0. So if we look from the left, so the graph, for what it's worth, I'll draw the graph over here. So the graph, until we get to 0, it's doing that number. Then once we get past 0, it's doing something like that. So from the left, we're drilling for oil. We're going down that way. So that looks like that is approaching negative infinity. On the other hand, we look from the other side and we try to close in from above, we fly off like Buzz Lightyear. Negative infinity and positive infinity, they don't match up. So the limit does not exist, but it's not approaching either of these. They don't somehow average out to 0 or anything like that. You could also use the LHB not equal to RHB thing if you'd like. But at this stage, I mean, saying that the limit doesn't exist, the function is unbounded, describing how the one-side limits behave, that's sufficient for our purposes. All right, the next example is a little bit more intricate, and I want to play around with it, so give me a sec to clean this off. All right, so in this next example, actually I guess the next couple of examples, because it's the same function, we just have left and right-hand limits showing up. So we have a rational function here with x squared minus 3x up top and x minus 1 living down below. So again, you can kind of tell the direct sub gives us a 0 denominator. I just erased my variable. And then I'm writing it in badly in return. Up top, we don't get 0 if we plug in x equals 1, so that's kind of a giveaway that there is going to be some kind of unbounded behavior in this instance, and we're going to want to dig in. So I drew graphs to support the last couple. For a moment, let's just pretend that our calculator's batteries have run out. Bear with me for just a second. My apologies for the delay. I've had to cough, and I figured you guys just didn't want to watch me do that. Anyway. So we're going to have like a vertical asymptote here. As it turns out, that's kind of a theorem if you go dig around in some math textbooks that a 0 denominator with a non-zero numerator indicates your graph is going to have a vertical asymptote there. Anyway, so what I'm going to do real quick is I'm just going to go ahead and factor this thing because it's going to be useful for something that I want to do. And it turns out that this particular method comes up often enough that I do want to, demonstrate it right here because it's going to keep coming up as the semester rolls on. So our calculator has died, so we can't just draw a graph like I did for the last couple of examples. That's a little more than I'm willing to try to put into it. And table of values, likewise, you don't want to start trying to punch in really small numbers into this thing. I mean, I guess you could, but anywho. So what I'm going to do is we're assuming that this limit is probably either positive or negative infinity just because of the whole 0 denominator thing. So what we can do to try to figure out what's going on is sketch out what you might have done in the past, something called a sign diagram. So the sign diagram here is going to be a number line. And I need to put some tick marks on here, and that's going to divide up my number line into chunks. The tick marks I need are any points of discontinuity in my graph. So x equals 1 is a point of discontinuity, just like we saw in the stuff in section 1.5. We also want to include any zeros of our function, or x-intercepts, places the graph would potentially cross the x-axis. So that would happen at x equals 0 and x equals 3 from looking at the numerator of this guy. So, okay, so now I've got those. Now I'd said a 0 denominator with non-zero numerator is generally a giveaway that there is in fact going to be a vertical asymptote. I kind of like to mark my diagram so I remember there's an asymptote right there. It's not strictly necessary, but I think it smooths things out. So now these 3 tick marks are the only places our function's sign could change from positive to negative or vice versa. Either it's got to go through the axis or there's got to be a jagged break like at this asymptote. All right. So now what we can kind of do is figure out what our function is doing in each of these 4 sections that are cordoned off. So for this first guy right here, we're off to this side of 0. Those are negative numbers, right? And I like to mark this over my factored function. So if our x value is less than 0, well, this guy is negative, thus the little minus. We're subtracting 3 from it, again, also pretty negative. Subtracting 1 more negative than we started with. So now all of these guys are being multiplied or divided together, so each pair kind of cancels out and gives us a positive, but we're still going to have a negative left over. There's an odd number of minus signs. So our entire thing has to be negative. That looks like a, yeah, twiddle, but you get the idea. There we go. Once I go past 0, well, subtracting 1 from something between 0 and 1, like 1/2, is still going to leave me being negative. Same thing here, but now this first term changes signs to a plus. And now I have positive times negative divided by negative. The two negatives would cancel each other out, and I switch to a plus. I like to write the pluses over the line and negatives and minuses below, but it's not necessary. And now I just kind of keep marching down the line. Between 1 and 3, like if you pick 2 as a test value, well, this is positive. 2 minus 3 would still be negative, but 2 minus 1 is now positive. So now I have positive times negative, that's negative, divided by a positive number, still negative. And then lastly, once I get past 3, you pick your favorite number, like 8675309. So now subtracting 3 from that gosh awful large number is irrelevant. So, we have positive, positive, positive. Everything's positive. The end result also has to be positive. All right. So now, what does that get us? Well, keep in mind, we're wanting to find the limit of this thing as we get close to 1 from the left. So we have to be on this side. And remember, you can sort of think of the vertical asymptote as something like a line you can't cross. So we can't cross the line, but we have to stay up above the axis. The only thing we can do is fly off to infinity and beyond. So that particular limit now from the left has to be approaching positive infinity. Our graph came through the axis, he's climbing, but he has to go up and up and up and up forever and ever. Similarly, if you look at the one from the right, if we try to work that guy out, now we're looking at what happens as we get close to 1 from the other side. And now we're stuck under the x-axis, and we can't cross this line. So we have to shoot downward in that direction. So that limit will in fact be negative infinity. We'll be approaching negative infinity. So I'm getting near the end of the time I have allotted for this video, but I do like to show this off. This is something that I like put on a projector in a classroom setting. So somebody sent me this picture a long time ago. I'm a big Lord of the Rings fan, so we get, I get Lord of the Rings stuff and vertical asymptotes all at the same time. Trying to make sure I show the little watermark for the website if you're interested. So yeah, Gandalf with his staff that looks like a lacrosse stick, telling the graph that it shall not pass. So yeah, welcome to my sense of humor. So that's it for this video. I'm going to dig in a little bit more on this. Play around with another one of these sign diagram examples just to mess with it, and then we'll take a look at some of the vertical asymptote stuff that's coming. So thanks for keeping on.